In this video, we're going to talk about matrix operations. We're going to define matrix addition, matrix scalar multiplication, define what it means to transpose a matrix. We're going to expand our knowledge from vectors into matrices. So what I mean by that is we're going to expand what span is in terms of matrices and linear independence in terms of matrices. In this section, we will start with something simple, and then we'll go to a more general set of information for matrices, and we'll see where that goes. So the first thing we're going to talk about is what a matrix is. A matrix is a vector space, m by n, and it's a set of all m by n matrices where entries form the set of complex numbers. Now, that's because we are in the complex numbers. Of course, that is true if it's real. We usually start with a larger set. We have matrix equality when each matrix is the same and that each matrix entries are the same. Now, I just want to talk a little bit about the fact that when we were doing our matrix, and so it was 1, 3, 0, and 2, and we did the row reduced echelon form, these were not equivalent matrices. They were not equal matrices. They had equivalents, but they weren't equal. So I did not, if you notice, every time I did that, I did not put an equal sign there. I put an arrow saying that's what they were row equivalent to, but they were not equal matrices because by definition, for them to have equality, they have to have the same numbers in the same positions. So just something to think about when we were doing the row reduced echelon form, and we made it when we talked about it in that form. Next thing we're going to do is define matrix addition. Basically, what this definition says is that I add the same positions. They have to have the same size. And whatever's in position 1, 1, I add to position 1, 1 in the second matrix, and etc. That's what matrix addition is. Scalar, matrix scalar multiplication means that I'm taking my scalar and it gets multiplied by every single entry in that matrix. So let's do a couple of examples here. So here is my matrices, and I'm asked to do the matrix addition. So I'm asked to do A and B. So I got to make sure they're the same size. To do the matrix addition, it is simply going to be adding this 1, 1 position to this 1, 1 position. That's going to give me 3. This 1, 2 position with this 1, 2 position, that gives me 17. This 2, 1 position to this 2, 1 position, it gives me 22. And lastly, for this particular example, I'm going to add the 2, 2 positions together, and so I get to 13. So that is my matrix addition. Matrix subtraction is just the scalar of -1 through the second matrix in this case, and then doing the addition. So I could have wrote this as 3c plus a -1 multiplied by d, so it still holds true. So the first thing I'm going to do is make sure that these are the same size, which they are, and I'm going to go ahead and multiply the 3 through as the scalar on C. So that means each one of my entries on my C matrix C will be multiplied by 3. This becomes 3, 15, 24, then that's going to be 276. So let's start putting those in there. So 3 times 1 is 3. 3 multiplied by 5 is 15. 3 and 8 is 24. 3 multiplied by 92 is 276. 3 multiplied by 12 is 36, and 3 multiplied by 6 is 18. And then I'm going to subtract off my second matrix, in this case happens to be D. And when I do that, I just make sure that my entries line up. So it's 3 minus this 10. So that first position is going to be -7. And then I'm going to do the 15 minus 14. That's going to give me a +1. 24 minus 7. That's going to give me a 17. 276 minus the 2 is 274. The 36 minus the 5 is the 31. And lastly, 18 minus 61 is going to be negative 43. So there's a couple of examples of matrix addition and matrix scalar multiplication. What we get in terms of matrices, the vector space properties of matrices, what that's saying is that we have the matrices, each one of the columns are vectors, and we get all of these properties. So it is closed. So if I have two matrices that are in the m by n matrix, that when I add them together, it also will be in the same size of matrix. We know that if we have some scalar multiplied by some matrix A, which is in the m by n matrices, that the scalar times that matrix A will also be included. We have the fact that we can add A plus B or B plus A. It is commutative. For addition, it is also associative, so I can add the first two matrices, like A and B first, and then add it to C. Or I can add B and C and then add that answer to A. So this is for addition. This is also for addition. We also know that if we add the 0 matrix that to any matrix, I get exactly what I started out with. We're going to get the additive inverse, which if I take A and add to it the additive inverse, the negative A, matrix A, plus the negative matrix A, I will get the 0 matrix. I also get the scalar multiplication associativity. So if I have two scalars, I can multiply the two scalars first and then multiply it by the matrix A. Or I can take one scalar, multiply it by the matrix A, and then take that answer and multiply that by the other scalar. We get the distributive property of scalars across addition. So I can add the two matrices first and then multiply it by the scalar. Or I can do the scalar onto each one of the matrices individual and then add those two matrices. We have the distributive property of scalar, so I can add the two scalars first and then multiply that by my matrix A. Or I can multiply each scalar by the matrix A and then add those answers together. Lastly, we have one matrices, which is if I take one and multiply it by its matrix, I get back to where I start. The proofs are, of course, in your book for your viewing pleasure. Now we're going to talk about what it means to transpose a matrix. The notation is A being the matrix and raised to the small little tree. That means that we're going to transpose it. What that means is my rows become columns, my columns become rows. Let's see what this means. So if they ask me to transpose my matrix A, my A transpose will be this. My first row becomes my first column, 1, 4, negative 2, 0, and 9. My second row becomes my second column, 3, 0, 1, 9, 11. My third row becomes my third column, so 2, negative 1, 7, 5, and 8. And there's going to be times in which we're going to want to transpose, and we now have defined what it means to transpose a matrix. When the matrix that I started out with is equal to its transpose, then we call that a symmetric matrix. So here's the theorem. Suppose A is a symmetric matrix, then A is square. So here's a square matrix. We're going to determine if it's symmetric. So what we do is we do B transpose. This is going to be 0, 4, 1, 3. That's my first row, becomes my first column. Now I can see that this column does not match this column with that transpose. So I can tell you that even though the matrix B is square, that it is not symmetric. But we'll go ahead and continue with the transpose. So the next one in the next column is going to be 2, 0, 7, and 8. The next column in the transpose is going to be negative 1, 3, 5, and 9. And of course my last column is going to be 8, 6, negative 4, and 1. In this case, I can tell you that B transpose is not the same as what I started out with, so it's not symmetric. Let's give an example in which we do have symmetry. So let's give you this matrix. We have 1, 2, and then I want to put a 2 here, and I might put a 5 here, and then 6 here. That means 6 needs to be down there. Then 4 and 4, and then 7. Now notice what I have is symmetry across that diagonal. That these two are symmetric, these two are symmetric, and those two are symmetric. So that would be an instance in which A transpose will actually equal A. So here's an example in which we do have a symmetric matrix. Let's talk about what we get with the transpose. So if I add the two matrices together and then transpose it, then it is going to give me the same answer as if I transposed each matrix individually and then added the two answers together. The next one we have is the scalar. So I can take a scalar, multiply it by my matrix, and then I can transpose it, or I can take and transpose my A matrix and then multiply it by my scalar. It is whatever one is going to be the easiest for you at the moment. And again, we are looking at the larger set, which is the complex numbers. For this example, they want me to find 3 times the transpose of the matrix A. So I can do it first as multiplying 3 times A, then transposing it, or I can transpose A and then multiply it. I'm just going to multiply it first. So I'm going to do 3 times A first. That's going to give me 3, 12, negative 6, 0, 27, 9, 0, 3, 27, 33, 6, negative 3, 21, 15, and 24. Now I'm going to go ahead and transpose this. So 3A transposed is going to be equal to 3, 12, negative 6, 0, and 27. The next column is going to be 9, 0, 3, 27, and 33. And my last column is going to be 6, negative 3, 21, 15, and 24. So that's an example in which we did a scalar multiplication and then transpose it. I would have gotten the same answer if I would have done the A, transposed A, and then multiplied it by 3. The next thing that we get is the transpose of a transpose is back to where you started. It's like the negation of a negation. You're back to where you started. So if you take your matrix A and you transpose it, and then you retranspose it, you get back to where you start. Cool? The definition of a complex conjugate of a matrix, suppose we have A as an n by n matrix. The conjugate of A is going to be A is going to be also an n by n matrix. Is going to be defined by this. So the conjugate of each individual piece is also the same thing as the conjugate of the matrix in and of itself. What the heck does this mean? Well, let's go ahead and do this example. Here, the conjugate of A just means that I'm going to conjugate each one of the entries. So my first entry is 2 minus I, so then I have 2 plus I as the conjugate. The conjugate of 3 is 3. We've talked about that in our last video. The conjugate of 5 plus 4i is 5 minus 4i. Negative 3 minus 6i. 2 plus 3i, and then of course 0. So there is my conjugated complex matrix. What we get from that, and this is going to be for the larger set, which is complex, which is going to be true for the smaller set of real numbers, that A and B are an n by n matrix, then I can conjugate the addition, or I can do the addition first and then conjugate the answer. That's what that's saying. And then if we conjugate a conjugate, we're back to where we started. So if I were to conjugate this, I would end up back to where we were started. Now we're going to, now that we've got some good foundations here, is we're going to continue with these ideas and these theorems into some more that follows directly from these theorems, but we're not going to use these until we get into the next section. But it makes sense to introduce them now because we're going to need them for the next section, which is the matrix indiverses of non-singular matrices. The first thing is we're going to define what an adjoint is, not Washington State adjoint. No, it is adjoint, or Colorado, because I live there too. How we're going to define that is if A is a matrix, then its adjoint is defined as A with an asterisk, which is equal to the conjugation transposed. We're going to show you what this looks like in the next video, in the next section. But for right now, I'm just giving you the definition. We will redefine the definition. The reason I need that is I need it for some of this information. Again, we're going to use this in the next section. Sometimes it's noted as ADJ of A or A raised to the H. The next theorem that we get that follows all of the theorems from above is that the adjoint of matrix addition. Suppose we have the matrix A and B of the size Mn. Then I can go ahead and do the addition first and then do the adjoint, or I can do the adjoint of each one individually and then add them. What we also get is the adjoint of matrix scalar multiplication. So as before, I can multiply my scalar times my matrix A and then find the adjoint, or I can do the adjoint of A and multiply it by the scalar. Last theorem for this section. The adjoint of its adjoint. So when you adjoint an adjoint, you get back to where you started. It's kind of like the transpose of a transpose. Whew. Okay, so that's it for the theorems. Now let's combine what we just learned to what we learned in the last chapter with vectors. So suppose we have this set where the B's are now a set of matrices of the same size. We want to find a linear combination. How do we apply the linear combination to this, and how do we determine whether or not we're linearly independent? How do we know if we have a number that's in a matrix C that is in the span? So let's take a look at our first example here. We want to show that this set is linearly independent. To do this, we're going to choose some scalars, just like we did before. So we take a scalar, and I'm just going to use the Greek letters. I'm going to do alpha times my first matrix, which is 1, 0, 0, 0. And then I'm going to add to it beta times my second matrix, which is 0, 1, 0, 0. I'm going to add gamma, multiply with gamma times my third matrix, which is 0, 0, 1, 0. And then I'm going to have my third matrix, or my third scalar, and I'm going to use delta. And it'll be by my my fourth matrix, which is 0, 1, 0, 1. 0, 0, 0, 1. And to show that this is linearly independent, it should equal, with this linear combination, the null space, or the zero matrix. So then what ends up happening is, let's go ahead and multiply this through. So I have alpha in this first position and zeros everywhere else. Then I have in here, I'm going to have 0 and beta and 0 everywhere else. So multiplying these are scalars. And then plus 0, 0, gamma, and 0. And lastly, I'm going to have 0, 0, 0, and delta. And you can see when I add all of these together, what I'm going to get is I'm going to get alpha, beta, gamma, and delta. And the only time that's going to equal the 0 vector is when alpha is equal to 0, beta is equal to 0, gamma is equal to 0, and delta is equal to 0. That's a terrible, terrible gamma. So the only time that's going to happen is when those each individual scalars are equal to 0. So we know that these are a linearly independent set of matrices. Okay, let's take a look at the next example. I want to determine whether or not these are linearly independent. So what I do is I'm going to use some sort of scalar multiple, and I did some fancy Greek letters up here. I'm going to make my life easy. I'm just going to use a sub 1s here. So if I multiply a sub 1 by my first matrix, which is negative 2, 3, 4, negative 1, 3, negative 2. And then plus, I'm going to add an a sub 2 and multiply it by my second matrix, 4, negative 2, 2, 0, negative 1, 1. And then plus a sub 3 multiplied by my next matrix, which is -1, -2, -2, 2, 2, and 2. Let's keep moving. And then we've got an a sub 4, which I'm going to multiply by the -1, 1, 0, then -1, 0, -2. And then, of course, I have one more. So I ran out of colors. So I'll have to go to black, plus a sub 5 times my fifth matrix, which is -1, 2, -2, 0, -1, -2. And then I check to see whether or not this is equal to the 0 vector of the same size. So 2 rows, 3 columns. What I end up with is I'm going to end up with this. When I multiply my A1 through, I'm going to get this matrix. My A1 times -2, my A2 times 4, my A3 times -1, my A4 times -1, my A5 times -1. So my first entry into my matrix is going to be -2A1 plus 4A2 minus A3 minus A4 and then minus A5. So all I'm doing is I'm taking and multiplying this scalar, each of these scalars, by the first position and then adding those numbers together. So this represents the 1, 1 position in this addition here. Now I'm going to go on to the next position. So it's going to be 3A1, then it's going to be minus 2A2, minus 2A3, plus A4, minus 2A5. So that is in the 2, 2, or the 1, 2 position, row 1, position, column 2. All right, let's do the next one. So it is going to be A1 times 4. So 4A1. And then 2. So plus 2A, 2A2. Lost the plot there for a minute. Minus 2A3 plus 0A4. And then lastly, for this last one is minus 2A5. Okay, so now I'm going to do my second row, first position, -A1 plus 0A2 plus 2A3 minus A4 plus 0A5. All right, now for my second position in the second row, it is going to be 3A1, -A2, plus 2A3, plus 0A4, plus, well, that should be a minus 2A5. Oh, minus 1A5. It's going to be bad if I didn't have the right one. So minus 1A5. Now I'm going to do my last position, which is going to be A1, -2. So -2A1, A2, 1, so plus A2. And then plus 2A3, then minus 2A4, and lastly minus 2A5. Whew! And we know this has to equal the 0 vector. Now what we do is we let each one of these entries equal to the 0 vector. So I start out with this one. So I have -2A1 plus 4A2 minus A3 minus A4 minus A5. And then I have this equation. Oh, and that equals 0. So that is negative a1 plus 0a2 plus 2a3 minus a4 plus 0a5 is equal to 0. My next equation is going to come from here. So it's going to be 3a1 minus 2a2 minus 2a3 plus a4 minus 2a5 is equal to 0. Then I'm going to do the next one from here. So 3a1 minus a2 plus 2a3 plus 0a4 minus a5 is equal to 0. And you see where I'm going here, right? You see that I'm going to be making the next one, my next two equations. So 4a1 plus 2a2 minus 2a3 plus 0a4 minus 2a5 is equal to 0. Last equation, negative 2a1 plus 2a2 plus 2a3 minus 2a4 minus 2a5 is equal to 0. Now what I have is a homogeneous system. So let's now throw this into another matrix where my first column will be the coefficients on a1. So negative 2, negative 1, 3, 3, 4, negative 2. My second column will be the coefficients on a2. So 4, 0, negative 2, negative 1, 2, and 2. My third column will be the coefficients on a3. So negative 1, 2, negative 2, 2, negative 2, 2. Third column, you guessed it, a4. So negative 1, negative 1, 1, 0, 0, and negative 2. Last column, the coefficients on a5. Negative 1, 0, negative 2, negative 1, negative 2, negative 2. Whoo, baby, this is good times. So now what we do is we RREF. And we look to see when we put in an RREF whether or not we have the same number of pivots as we have columns. So if we have the same number of pivots as we have columns and we don't have any of these to be free variables, then we know that we have linear independent sets of matrices. So there's that. All right, matrices within matrices. Let's take a look at this next example, and they're asking us to determine whether or not A is in the span of S. So we know that from up above, my span S is the same thing. Notice that this is this. This is this. So I know that these are linearly independent, and I also know that this is the smallest subset that I'm going to get. I can't get any smaller than this to generate my span because they're all linearly independent. I know that from my last chapter. So what I do is I set it up just like I did before. And same kind of shenanigans as I did here. But when I do these shenanigans, it's going to equal those entries in the matrice. So instead of having my first equation equaling 0 right here, it's going to be equal to this negative 13. So in other words, what I'm going to do is I'm going to augment onto my matrix these numbers. And I'm just going to make sure that I put all of these numbers in the right places. And I would do that here. And then I would put it into my RREF form, and I would make sure that when I did my augment, I'm going to augment on here now the correct numbers that are associated with each one of these entries here. So I'm just going to go through it really, really fast. My first equation, which was this one, it needs to be the negative 13. So let me erase this. So we know that this needs to be, erase this. So let me erase all of these here because I'm now going to, instead of have them equal 0, I'm going to have them equal those entries of that matrix. So let me just move this if it feels like playing. Okay, there we go. There we go. So let's go ahead and erase this. And so my first row, my first set of equations came from the 1, 1 position. So I'm going to have this equal the negative 13. That's what I'm going to augment onto, is that negative 13. My second equation was equal to the 1, 2 position, so this needs to be equal to negative 8. The order doesn't matter how you write your equations, but making sure that they equal the right numbers here will matter. The 3a, negative 2, and then 2, and then all of that should equal the 24 because it came from the 1, 2 position. So this needs to equal 24. The next one needs to equal the negative 2. And then, of course, my last ones where I've got the 4 and then the 4a1, a2. This needs to equal the 2, and this needs to equal the negative 20. So once I do that, I go over here to my matrix and I augment on those numbers in the right places, RREF, and I'm going to get an answer. And in fact, what I know for this, my A1, when I get done doing it, so you shouldn't go through this, but when I get done, my A1 is 2, my A2 is negative 2, my A3 happens to be negative 3, my A4 happens to be 4. So I've got all of the numbers that I need to multiply this 1, 2, 3, 4, 5, and I will get this. So this is one of the ways in which of getting this answer. Okay. Now let's take a look at our last one. What they're asking us to do is, suppose we have Y, which is a set of all 3 by 3 symmetric matrices. We want to set T so that T is linearly independent and that the span of T is Y. The easiest way to do this is to do what we did from our very first example. If you remember from our first example, we went ahead and went through the matrix in which I have a 1 in certain positions, right? Well, I want this to be a symmetric matrix. So if I put a 1 here and zeros everywhere else, here's my first one, which will be symmetric. The next one that will be symmetric is if I put a 0 right smack in the middle. Excuse me, a 1 right smack in the middle. The next one that I'm going to get that is symmetric is a 1 down in the lower corner. Now, if I put a 1 in this position and everywhere else zeros, then I have another one. So 0, 1, 0, 1, 0, 0, 0, 0, 0. Here's another symmetric matrix. Similarly, if I now put the ones down here, so I have 0, 0, 0, 0, 0, 1, 0, 1, 0. This is also in my matrix. And then my last one will be zeros or ones in each one of those diagonals. So 0, 0, 1, 0, 0, 0, 0, oh, that should be 1, 1, 0, 0. Basically, what I'm doing here, let me go ahead and do this, is I am taking an A, a B, a C, a D, an E, an F, a G, an H, and an I, and I'm ensuring that I'm getting every combination which will be linearly independent, and it will get the entire set. So I have a 1 in the A position, a 1 in the E position, and 1 in the I position. And then I need something here in the D and B positions that have to be the same. I have to have something in the G and C positions that are the same, because that way I can make sure that I get something in those positions, because if I don't, I'm going to get zeros. And then, of course, in the H and F, I need something in those so that if I were to add all of these together, if I were to add all of these matrices together, then I'm going to get a matrix that is full of 1s that's going to be square. So that's it for this section.